Hello there and welcome back to this video series on control systems. In the past video we have seen the frequency characteristics of lag compensator, and we have seen that lag compensator is a low pass filter. It would be helpful if you watch videos 55 to 63 before watching this video to make the most out of it. After watching this video, you'll be able to design a lag compensator. We have seen that the structure of the lag compensator is similar to that of the lead compensator. You have a zero of the compensator, a pole of the compensator. We write the zero as s plus 1 over tau and pole s plus 1 over beta tau with beta greater than 1. The sinusoidal transfer function of the compensator is written like this. We will see this compensator with the help of body plot. If you draw the body plot of this, you will see that there is a valley here giving minimum value of phase, that is you get up to minus 60 degrees added to the phase, and also you see that this magnitude curve gives an attenuation of 20 log to the base 10 1 over beta, where beta is the factor given over here. We will use this fact later in the design. Without much delay, we'll try to consider this lag compensator with the help of an example. We are required to design, let us say, a compensator for this transfer function, and we have the design specifications as phase margin is 40 degrees, required gain margin is 10, and we want a velocity error constant of 5 second inverse. We begin by drawing the body plot of this transfer function, and we see that the gain margin turns out to be 9.54 and the phase margin is 32.6 degrees. And we saw that both the gain margin and phase margin requirements are not satisfied. We see that the velocity error constant given by limit of SGS as S tends to 0, this is computed to be 1. So we saw that the steady state error constant is also not achieved. We'll first try to fix this problem by choosing a compensator, a proportional compensator, that is compensator is constant K1. With this compensator, the open loop transfer function is K1 multiplied by your plant transfer function. This is the transfer function of the compensator. This is the transfer function of the plant. With the open loop transfer function given here, you find velocity error constant Kv, and it turns out to be K1. So if we want Kv to be 5, we see that this K1 should be 5. So with this choice of K1, the proportional controller, we have the open loop transfer function as given by this 5 in the numerator. And we draw the body plot for the transfer function with gain adjusted to be 5. So you see that the gain margin deteriorated, the phase margin deteriorated. The velocity error constant is achieved. But that doesn't really mean anything because the system is already unstable. From the body plot shown in the previous slide, the gain and phase margin are deteriorated and the system is unstable. So we consider designing a compensator of this form, that is both a constant term and a dynamic part. Since we want the phase margin to be 40 degrees, find the frequency at which the phase is minus 140 degrees. We'll show it on a graph sheet in a little while. And we find that the frequency is 0.632. And we want this frequency to be the gain crossover frequency. And we say gain crossover frequency occurs when gain is 0. But we see that the gain happens to be 16.2. Thus, we need to bring the curve down. By 16.2 dB, or the dynamic part needs to provide an attenuation of minus 16.2 dB. And we already saw this we achieve if you choose beta such that 20 log to the base 10, 1 over beta is minus 16.2 and beta is 6.3. And we choose the corner frequency to be 0.1. Okay, let us see these on a graph sheet to make things a bit more clear. This shows the body plot for the gain adjusted system. That is, gain is chosen to be 5. And you see the gain margin reduced, the phase margin reduced, and thus we want to design a compensator. We want the phase to be at minus 140, and this happens at 0.632. Project this 0.632, you see that the gain is 16.2. If 0.632 were to be the gain crossover frequency, you need to bring the curve down by 16.2 decibels so that it passes through 0. If the curve passes through 0, this is the gain crossover frequency, and the angle here is minus 140 and the phase is 40 degrees. Though we show the curve moving entirely by 16.2 dB down, actually what happens is the curve shapes itself so that it passes through 0. So we have chosen this to be 0.632, and with this choice of the choice of beta and tau, we see that the compensator comes out to be 5 into 10s plus 1 by 63.1, and the open loop transfer function is GGC, which is all this. The body plot of this transfer function is shown in the next slide here. We see that the gain margin improved substantially, the phase margin improved substantially, and Kv, of course, the velocity error constant, of course, is still 5. We are not changing that. We wanted a phase margin of 40 degrees, but we got only 32 degrees. So a little bit of tweaking is still required. So we choose a phase margin of 52 degrees with the hope that if we want it to be 52 degrees, it will turn out to be 40 degrees in the end anyway. Because when we want it to be 40 degrees, it came out to be 32 degrees. So let us choose it to be 52 degrees, and it may fall down to maybe 42 degrees or 40 degrees. That is, we are aiming high, much higher than what we want. So we choose the frequency at which the phase is minus 128. Okay, so minus 128 minus 52 is minus 180. And this occurs at 0.465 radians per second, and the magnitude at this point is 20 decibels per decade. So the compensator needs to offer minus 20 dB as shown here. The frequency at which the phase happens to be 52 degrees is given by 0.465. radians per second, at 0.465 radians per second, it is 20 dB. So you need to bring the curve down by 20 decibels. So the compensator needs to offer minus 20 dB. Again, note that though I have shown the curve to be translating, actually the curve shapes in such a way that it starts here and gradually droops down and passes through 0 dB, because we want the gain at 0.465 radians per second to be 0, not the whole curve shifting down. If you want to shift the whole curve down, you need to change the gain. In any case, we have chosen beta is equal to, we computed beta is equal to 10, and with this value of beta, the compensator is given here, and the open loop transfer function is given here. Okay, plant multiplied by compensator. Note that we are keeping this 5 all through. Because we are keeping this 5, kV is equal to 5. That fact is not changed at all. We'll try to draw the body plot for this compensated gain adjusted open loop transfer function, which is shown in the slide over here. With this, we see that the gain margin is satisfied and the phase margin is satisfied. All the things are satisfied, and we are good at this stage. If we want to be extra cautious, this is not expected in your examination because it is very difficult to draw the step response of the system in an examination setting. So I will just show it here, but you don't have to do it during your examination. We will see that the system is very slow, with a settling time of around 15 seconds, and we need to do considerably more work to improve this situation. This I'm leaving. As I told you, this you don't have to do it in your examination. You see that it is coming within the 2% tolerance band, somewhere at 15 or 18 seconds, which is very slow. If a system takes 18 seconds to respond, nobody would want to have such a system. We want the system to respond in a snap, but that is not happening here. To change it, considerably more work may be needed. So we will stop here. We say that we are satisfied with this design and we stop. And thus, we have summary as shown here. A lag compensator is a low pass filter. It gives sufficient phase margin, and the pole and zero of the lag compensator are chosen close to each other. The lag compensator reduces the bandwidth and the settling time in a little way. That is, settling time becomes more and bandwidth becomes less, which is okay from noise perspective, but it is all the same a trade-off. We need to do a little bit more work, but that is not expected here. That's all we have for now. Have a great day.